Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy at Foothill College, and it's my pleasure to welcome everyone viewing us in the United States and around the world to this lecture in the 22nd year of the Silicon Valley Astronomy Lectures. These non-technical talks are sponsored by 4 astronomical organizations: the Foothill College Science, Technology, Engineering, and Math Division, which includes the astronomy program, the SETI, or Search for Extraterrestrial Intelligence Institute in Mountain View, the Astronomical Society of the Pacific, and the University of California Observatories, which includes the historic Lick Observatory. And we're very grateful to all these organizations and to all of you for your support. I want to remind everyone that we have new lectures coming up all the time. And if you'd like to be notified when new lectures are uploaded, you can subscribe on this YouTube channel where you're viewing the lecture right now. We urge you to subscribe. And when you do, we want you to click the notification bell, because without that, YouTube won't send you the notifications of new lectures. And we don't sell the mailing list, so you won't get spam as a result of signing up. I also want to encourage everyone during the lecture, if you have questions, to email them. We don't have an active chat window, but we do encourage you to email your questions to astronomy@foothill.edu, astronomy@foothill.edu, and that will come up on the screen during the evening. So feel free to do that. Tonight, we're going to talk about one of the most exciting parts of astronomy, the universe, the invisible universe of brown dwarfs or failed stars. And our speaker tonight, I'm delighted to say, is Professor Adam Burgasser, who's Professor of Physics at the University of California, San Diego, and an astrophysicist who studies the coldest stars, these brown dwarfs, and planets orbiting other stars. Professor Burgasser defined a class of these brown dwarfs while he was still a graduate student, and is one of the co-discoverers of the most intriguing system of exoplanets called TRAPPIST-1. This is a system of 7 Earth-sized planets orbiting an object which is at the boundary of stars and brown dwarfs. Professor Burgasser has authored over 600 publications, including work in astrophysics, in physics education, and equity, diversity, and inclusion. He is currently serving as a vice president of the American Astronomical Society, which is the professional organization of astronomers in the United States, and he's been a Fulbright scholar. So, ladies and gentlemen, it's a privilege for me to present talking about Dark Star, the invisible universe of brown dwarfs, Dr. Adam Burgasser.
Thank you very much, Andrew. That was a wonderful introduction, and I really appreciate that you've actually already hit some of the highlights of the talk, so folks know what's coming. That was really great. Welcome, everyone. My name is Adam Burgasser. I am a professor at UC San Diego, and I'm very pleased to talk today about my favorite subject, which is brown dwarfs. I'm going to go ahead and share my slides so you can see what they look like. So as Andrew mentioned, the title of my talk today is Dark Star, the Invisible Universe of Brown Dwarfs. And we're going to kind of decompose that title a little bit to understand why this particular class of objects could be considered a dark star and what that really means, and why they have this unusual property. And we're going to then go into how that unusual property of these objects and their abundance in the galaxy means that they're going to be a very important tool for studying not just the region around the sun, but the Milky Way and potentially the whole history of the universe at large. Big issue. So let's dive in now. Before I get started, I do want to take a time to do a quick land acknowledgement. I am giving this talk from my home in San Diego. And San Diego is in North County, San Diego, California, North County, San Diego, California. And that land is the unceded territory of the Kumeyaay Nation. Today, the Kumeyaay people continue to maintain their political sovereignty and cultural traditions as vital members of the San Diego community. So I acknowledge the Kumeyaay people's tremendous contributions to this region and I thank them for their stewardship. And if you want to learn more about the Kumeyaay people and the land acknowledgement for both my home and for UCSD, there's a link there to our UCSD Intertribal Resource Center. So this talk is about brown dwarfs. So I think the first thing we really need to get down to is, what are these things? What is this strange phrase of brown dwarfs? And as I mentioned, this is going to talk about, kind of touch on a few different topics in astronomy and physics in general. In particular, to understand what brown dwarfs are, we have to understand a little bit about the physics of stars and the physics of cool atmospheres, atmospheres of stars and planets. We're going to be putting this into the context of both the immediate neighborhood of the sun, what are the sun's nearest stellar neighbors, and how do brown dwarfs fit into that picture? And also in the context of potentially habitable worlds. Andrew mentioned TRAPPIST-1 at the beginning. We're going to mention that a little bit later on in the talk. But even like more dense physics topics, so things like exotic states of matter. As we'll see, brown dwarfs are extremely dense bodies, and they can possess very exotic states of matter that we can't actually study in laboratories on Earth. So these are places where we can see some states of matter that are completely unique to our ability for laboratory science, and also the nature of dark matter. And finally, I will hopefully convince you that brown dwarfs are also very key to understanding even bigger pictures about the formation, the history, and ultimately the fate of our Milky Way and the universe at large. And that's going to be based on the fact that brown dwarfs, we're stuck with them. Once they form, they're around forever. So we'll see how that comes out in just a moment. So I'd like to start by kind of putting this into kind of some basic astrophysical or astronomical terms. And probably the best place to start is just thinking about, how do we actually observe stars? What are the things when we look at stars, like the stars in this beautiful picture of the Milky Way, how can we characterize them? Now, this is not a give and take talk, so I will let you think about those answers to yourself. I will say when we talk about it in the class, the first kind of obvious things when I look at an image like this is that all those little points of light, we can quantify things like the brightness. How bright is the light? How dim is it? And also there's a little bit of color to these stars, right? You can see some of them are a little bit purplish red, some of them are a little bit blue. And of course, where they are in this image and how in some regions they're very densely clustered, in some regions that they're very sparse. All of these are pieces of information that allow us to kind of build up a bigger picture about stars and their sort of distribution in our galaxy. There's other things we can measure, like their distances, which we do through parallax. Their motions in the sky. We think of stars being fixed, but in fact, they do have velocities, and so they move very small amounts of angle over every year, depending on how close they are. We can also measure their spectra, the distribution of light as a function of wavelength, how they vary with time, et cetera, et cetera. We're going to talk about all of these different concepts as I introduce the basic core things about brown dwarfs. But again, these are kind of the observables. These are the things that we can directly measure for the stars in our galaxy. Now, when we combine those measurements, we start to see some really interesting and unique patterns that really get to the physics of what stars are. So what I'm showing you right now on the upper left corner is an image of the Omega Centauri cluster. This is a 11.5 billion-year-old globular cluster that's about 15,000 light years away from us. And it contains some of the oldest stars in our galaxy. The foreground image is a picture taken of that cluster with the Hubble Space Telescope. And you can see very dramatically these kind of red and blue stars of different brightnesses throughout. Now, this is a visualization done by a colleague of mine, Jay Anderson at Space Telescope Science Institute. And I'm going to show what happens when we organize our stars based on color and brightness. So what's happening in the animation is we're pushing all the red stars to one side, all the blue stars to the other side, and we're kind of organizing that way. And now we're going to rotate the image so all the bright stars are at the top and all the faint stars at the bottom. And we started off with kind of a random jumble of stars. When we do this organization, we end up with this beautiful pattern instead, right? And this pattern is known as a color magnitude diagram, because that's how we organize the stars. And so literally if I put some, oops, sorry, I apologize, I'm gonna have to run the simulation again, which is a great simulation, so you get to see it again. So again, we're sorting the stars by color. We're gonna sort the stars by brightness, and they're gonna end up in this pattern, which is a classic diagram that we use in astronomy called the color magnitude diagram. There's all kinds of information that's in this diagram, things about what types of stars we're looking at, the age of the system that we're studying, this globular cluster, the composition, all these things. when we study these stars, we can actually identify different classes of stars in here. So for example, our lowest mass stars are down here at the lower right. Stars like the sun are kind of in the middle here. And this kind of turnoff leads us to bright red and also bright blue stars. And these turn out to be stars that have evolved off this main line, which we call the main sequence, and are on the way to stellar death. All right, so don't worry, the objects we're studying today never die. So that's actually a nice, happy story. But most stars will run out of hydrogen and they evolve off this main sequence and become giant stars and eventually compact objects. All right, but this pattern comes again from organizing the colors and brightnesses of stars. And if we focus on this kind of diagonal line here, this main sequence, which are our normal stars that are fusing hydrogen in their cores, we can organize those again into different categories based on their brightness and color. And in fact, we organize them based on something called their spectral types, which is a measure of the sort of shape and morphology of their spectrum. We'll see some of those spectra a little bit later on. But since the 1940s, we've had this organization of stars that run from the biggest and brightest stars that we call O stars down to the tiniest little stars that we call M dwarfs. You might ask, why do we have this odd sorting of letters? Are astronomers able to spell? What's going on? We could talk a little bit about that maybe in the Q&A, why the order of letters is this way. But the stars can kind of be organized again along that main sequence by their brightness and color. And that turns out to match up with their size and their mass. So these bright stars, blue stars, tend to be much bigger than the sun and much more massive, about 40 times more massive than the sun. Our sun is one of these little yellow stars. It's called a G dwarf. And the smallest stars in this diagram are the M dwarfs. And these are about 10% as large and 10% as massive as the sun. So a pretty broad range of masses and sizes. But again, this comes from measuring their brightnesses and colors. Now, where do these come from? Well, they ultimately come from even bigger structures. And of course, these are our star-forming clouds, these star-forming regions. One of the most famous of which, of course, is the M16 Eagle Nebula. This was the subject of that classic Pillars of Creation in the early Hubble images. This is a more recent Hubble image showing the full sort of cloud, at least a kind of stigma of this cloud coming off in beautiful detail. All of this is gas and dust that's actively forming stars. In fact, many of the stars are actually hidden inside their little cocoons of gas and dust. Now, it's important to keep in mind that these are big structures. This little thread is about 10 light years across. Just to keep in mind, our nearest star to the sun is about 4 light years away. So this is bigger than the distance between us and our nearest stellar system. So these are the structures where stars come from, and this actually gives us a clue to how these stars actually get to the point where they are fusing hydrogen. So I'm going to start with what we always do in physics is we simplify this beautiful, gorgeous structure with a sphere, which is totally wrong, but we'll do it anyways. If we take a little piece of that cloud, maybe about 1/10 of a light year across, what happens to these clouds is that at some point they collect enough mass and they cool off enough that the competing forces of gravity and thermal pressure, gravity eventually wins. And so as these things radiate and cool off, gravity pulls them together. And as it does so, the heat released from that gravitational infall, much like the sound that you might make if you dropped your keys on the floor, that is turning into heat inside the star. Half of that heat goes into heating the star, half of it gets radiated off so we can actually see these things. And that is increasingly making the insides hotter and hotter and hotter. At some point, it gets so hot that you can start to fuse hydrogen. And I mean, it has to get really hot, millions of degrees Kelvin, before those fusion reactions can kick in. But once they do, releasing that nuclear energy is able to essentially increase the thermal pressure and stop the collapse of the star. And that's what's setting roughly the sizes of these stars. As they shrink down, nuclear reactions kick in, and that basically halts the contraction. And so for something like the sun, that halting of the contraction happened roughly around the size of the sun, the diameter of the sun. That's why we have these suns of these sizes. If you have less mass in a star, a smaller mass star, then you have to actually shrink this down even further to extract enough heat to kick in those nuclear reactions. And so this pattern of large mass, large size and large mass stars and small size and small mass stars has everything to do with the fact that you need to get enough heat from contraction to start those nuclear reactions, which is the main job of a star, right? It's the energy that's outputting from its surface is ultimately coming from hydrogen being turned into helium. So at low masses, very roughly, the mass and the radius are proportional to each other. Now, in fact, it's not even rough. It's actually pretty close. This is a beautiful set of measurements that are made with a facility actually in Los Angeles called the Chara Interferometry Array. This is a facility that's able to measure the radii of stars directly through interferometry. And my colleague, Tabitha Boyajian, was able to measure the radii of stars across this range between about 1/10 of a solar mass and 1 solar mass. And there's almost a perfect 1-to-1 match. This dashed line is, solar radius is equal to solar mass, and it fits almost perfectly. All right. So you can ask, and people have asked, how far can this go? Right? If we go down to 1/10 of a solar mass, we get 1/10 of the radius of a star. What if we go to 100th of a solar mass or 1,000th of a solar mass? How small can we actually make these stars? Now, this is not a academic question because there's another important aspect of stars that's important to know, and that's the number of stars as a function of their mass. So I'm going to give you another quiz you're going to do on your own because I can't take any answers on the chat here. Of these types of stars, which do you think is the most common class of star in the galaxy? And I'll give you 2 seconds to think about it. 1, 2. All right, the answer is it's the little ones. All right, 70% of all the stars in our galaxy are in this tiniest class of stars, these M dwarfs, right? So they may be small, they may be red, it may be hard to see, but they are the most abundant star that's out there in the galaxy. And that's actually something that's been known for a long time. In fact, one of the first indications that that is the case, that the smallest mass stars are the most common, came way back in the 1950s through a study by Edwin Salpeter, who's very famous among astronomers because he was the first to measure something known as the mass function, or the distribution of stars as a function of mass. Now, this is actually from his 1955 paper with a little illustration on top of it. But what is plotted here is mass of star on the bottom, and this is in log units. So solar mass here at solar mass here at 0, 10 times the mass of the sun at 1, and this M star is about 1/3 of a solar mass. And then the axis on the right, the vertical axis here, is the number of stars per sort of mass bin, but again in factors of 10. So if you read this correctly, if we go from sort of solar type G stars up the M dwarfs, it's a factor of 10 increase in number, very roughly. So there's a lot more little stars than there are big stars. And so they are very much the most common class of star in our universe. Now, I said, they can be small, they can be very abundant. They seem to be going up as we go to smaller masses. How far does this go? Right? And this was a real question back in the 1960s because there was an outstanding problem that is still an outstanding problem today. And that question is, where's all the mass? All right. So when we look at the how stars orbit around galaxies, when we look at how galaxy clusters are able to lens the galaxies behind them, we know from both of those measurements that there's a lot more mass in galaxies than we can actually see. And we have a word for this, is dark matter. You've probably heard of this many times before. But these are the observational clues that we're missing, something like 80 or 90% of the mass in our galaxy. We just don't know what it is. And we still don't know what it is. But, and this is, if you're into the Nobel Prize game, this is up for grabs, right? We've got tons of Nobel Prizes for regular matter, right? They give them out every year, right? No big deal, right? We got one Nobel Prize for dark energy. That's very exciting. But no one's gotten a dark matter prize, right? And this is a big opportunity, folks, big opportunity. All right, so the question is, can this just be in small stars, right? How small can you make these stars? Because if you make them really small and you make enough of them, maybe that's dark matter. And that was a real question back in the 1960s and 70s when people were trying to understand the nature of dark matter. Maybe it's just dark stars, really tiny dark stars. Now, there is a limit to how small a star can be. If you think about it, logically, actually having a star that you can hold in your hand seems, pretty optimistic. At some point, you're going to have to squeeze things so small to get them hot enough that, you're kind of getting smaller than a proton. In fact, if you get down to kind of the size of a bus, you have to shrink that down to a mass smaller than a proton, which you can't do. So there's got to be a limit, right? So where is that limit? And that was a question, a theoretical question that was really up in the air in the 1960s. Now, it turns out that that limit comes not from thermal pressure or from gravity or from fusion, but from a completely different area, which is quantum mechanics. And in particular, an idea called quantum degeneracy. And this is an idea that's articulated in the 1920s. And this is, for example, what Wolfgang Pauli said about degeneracy, is that no two identical fermions, which are particles with half-integer spin, can occupy the same quantum state simultaneously. Now, that's a lot of physics speak. So let me translate. Basically, you can't put two things in the same place at the same time, all right? Because most of the things that we're talking about are fermions, electrons and protons and stuff like that. Now, it's not quite that, right? Because if you can't put two things at the same time, that's kind of like subway degeneracy, right? If you're trying to shove people in the subway, right, there's just a limit. You can't get any more people in there. Degeneracy at a quantum scale is actually a little bit more complicated, and it's probably a little better tuned if you think about parking lots, right? And I got this great analogy from the Harvard Chandra X-ray Center. So those of you who get to live in California and drive around and try to find spaces in parking lots know that when you go to a parking lot that's nice and empty, piece of cake, right? I'm just going to find a nice empty spot, pull in, no stress. But usually when you're going to the grocery store, all of the parking lots are full because everyone's driving over there. And you're hovering around trying to find that spot. You got to speed up to beat someone else to it, right? There's a lot of activity going on in order to fight for those last little spots. And that's really more analogous to what's happening with the kind of degeneracy that holds brown dwarfs up. And this is actually the electrons are doing this. The electrons are trying to go down into the coldest spots, the lowest energy spots that they can occupy, but they're all occupied. And so they're just running around crazy because they can't get rid of their energy. And all that crazy running around produces a pressure, right? And that pressure is what actually starts to hold up stars when they get to a certain amount of density as they're contracting down, all right? So it's not thermal pressure, it's not nuclear power that's pushing them out. It is this quantum mechanical principle of degeneracy. So this was something that was discovered and studied in the 1960s, and one of the discoverers of this idea theoretically was Shivakumar in 1962. This is actually a picture of him at the 50th anniversary of his paper. And this again is a plot from his paper, and what it's showing is in his theoretical calculations, he's taking a ball of gas and he's shrinking it down, so it's getting to higher density and higher temperature. So these lines are showing those tracks. They're moving up in this direction. And this line, this blue line here on this plot, is showing the point where electron degeneracy starts to kick in and halts the contraction, right? It provides a new source of pressure to prevent things from collapsing inward. And when you get to below a certain mass here, and it works out to be about 7% of the mass of the sun, the object basically is stopped from collapsing before it can get hot enough to start hydrogen fusion reactions, right? Again, so that needs to be about 3 million Kelvin. And if degeneracy stops the collapse before it gets that hot, you have an object that will never get hot enough to fuse hydrogen. And that's why we call it a failed star, because it actually fails to do the thing that stars do, which is actually to fuse. Instead of hydrogen fusion providing the pressure to hold up the star, it's this other quantum force called quantum degeneracy pressure. So this was discovered in the 1960s, and they were actually able to predict exactly what the mass was. It's about 7% of the mass of the sun. They were also able to predict pretty well what the sizes of these objects would be. And it turns out they'd be about the size, in fact, a little bit smaller than the size of the planet Jupiter, our biggest planet in our solar system. So way back in the 1960s, we had a prediction that, yes, these objects could exist. They'd be really low mass. They'd be really small, so hard to see. And they wouldn't be fusing hydrogen, so they'd be very hard to see for that reason as well. So these are, these failed stars are brown dwarfs. Now, failed stars seems like that makes sense. Brown dwarf seems like an odd term to come into being. And I can say, and this is a great opportunity to plug SETI, because that phrase actually comes from SETI's chair emeritus, Jill Tarter. Before she went off and did amazing things looking for extraterrestrial signals, her PhD thesis was looking for and understanding the atmospheres of brown dwarfs when they were still theoretically conceived. And as part of her thesis, she coined this term brown dwarfs. And in an article that she wrote some time ago, she said that, we need to have a color because, stars have colors. We talk about stars like the sun are yellow dwarfs, and stars that are really low mass are red dwarfs. These aren't red, right? They're cooler than that. And they're not really black, right? Black is nothing, right? You got no light coming out of it. And so Jill proposed brown as the color to kind of encompass not just the kind of in between, but the fact that these would be all kinds of colors as they evolve, as they cool. So a great inclusive name for a color, and that's where this name came from, and it has stuck all the way to this day. So thank you, Jill, for that phrase. Now, so we've got this candidate for dark matter, right? So wow, people must be going out like crazy and trying to find them. And so 1960s, we got this 3-hour prediction. This thing must exist. Let's go and find it. And we didn't find any. All right, but that's okay, right? We try. We'll build bigger telescopes. We'll develop more sensitive instruments, and we still didn't find any. And 1980s, there was one brown dwarf that was reported. And it was very exciting. And I actually remember as a child watching Good Morning America and seeing the discoverer of the first brown dwarf talk about these Lilliputian stars and these tiny failed stars. And unfortunately, it turned out to be a imaging artifact. So there was none, right? So 3 decades, nothing, right? And so people started to ask, well, maybe they just don't exist. In fact, you can look at papers in the 1990s that argue very convincingly that the physics of star formation are such that brown dwarfs simply cannot be formed. There's just no way to make them. But there's an alternate explanation. Not that they don't exist, but they just aren't visible, right? And one thing, I want to go back to our kind of map of different kinds of stars, right? So we talked about really bright stars, big massive stars are bright and blue. And the coolest stars at the other end are faint and red. So temperature is a key term here, right? The hottest stars are blue. The coolest stars are red, all right? And this actually, if you think about it, it's opposite what we think. We think of blue as being a cool color and red being a warm color. Totally opposite when we actually look at the actual colors of stars and their temperatures. Now, I've been talking about brown dwarfs as being things that cool off over time. And in fact, the predictions from these evolutionary models are that when they're really young, so this is showing the surface temperature as a function of age. So early on, when they're just kind of little baby stars and baby brown dwarfs, these objects are relatively warm. So something like 2,000, 3,000 Kelvin. That seems really hot to us, but that's just kind of warm for a star. But when a star evolves and kicks in nuclear fusion, it ends up staying at roughly that same temperature. So our lowest mass stars get to about, again, like 3,000 Kelvin, and then they just stay there because all of the energy they're losing through radiation is being made up through fusion in their cores. Brown dwarfs don't have fusion. So as they radiate their energy away, they just cool off, and they just cool off continuously over time. And you can see that for just this one model, that temperature gets down to about 1,000 Kelvin, which is darn right frigid for a star. And so if these are red dwarfs, you have to ask, what's redder than red? Because these are going to be much cooler because of this cooling effect. And so if you know your electromagnetic spectrum, you know there is a redder than red. There is infrared, right? So here's our kind of standard educational picture of the electromagnetic spectrum, the tiny sliver in terms of wavelength that we can see with our eyes, the visible spectrum running from red to purple here. But then on other sides of this, we have invisible forms of light. To the high energy end, we have ultraviolet, X-ray, gamma rays. To the low energy and long wavelength, we have infrared, microwave, and radio. So infrared is the redder than red. And so if we're looking at things that are cooler than red dwarfs, what we really want to look for are infrared dwarfs. And for that, we need infrared cameras. Now, I want to do another analogy of this because I'm here in San Diego. We love to go to the beach. There's lots of fun things you do at the beach. You look at the sun, you look at campfires. And actually, those two objects are really good examples of how this balance between infrared and visible. So we think about the sun. The surface of the sun is about 6,000 Kelvin, about 10,000 degrees Fahrenheit. And the sun, if you think about it, is more bright than hot. And when I say bright than hot, you don't want to stare at the sun because the visible light can totally burn out your eyes, right? But you can stand under it and stay nice and warm, and it feels, gets you nice and warm in a cold winter day. All right, so that warmth you're feeling is kind of some of the infrared radiation. A campfire is much cooler, right? It's about 800 Kelvin or so, about 1,000 degrees Fahrenheit, depending on what part of the campfire you're looking at. Campfire is much hotter than brighter, right? So you can stare at that campfire and think deep thoughts all night long, but don't lean in too close, so you'll singe your eyebrows, all right? So there's a lot more heat, feeling the heat coming from the campfire than actual brightness in your eyes. And so this difference of temperature really does shift where the light comes from, whether it comes in visible light wavelengths or infrared wavelengths. And as we go to even cooler temperatures than the sun, increasing this light is coming out at these invisible infrared wavelength bands. Now, when we look at the universe, we see amazing things in the infrared, and we really see a completely different universe at these different wavelengths. The left image here is an optical image, nice deep optical image of a region around the Orion constellation. You can see it outlined here. Here's that beautiful Orion cluster in the belt. When we look at the same sky with an infrared telescope, in this case, the Akari telescope, looking at it at 140 microns, it's a completely different picture. What we see is these gorgeous columns of gas. We see these bubbles that are coming off of this bright star here. And we see these star-forming regions, the Orion Nebula Cluster and others, glowing in this beautiful infrared light. Right? So by looking at different wavelengths out in the sky, we end up seeing a lot of different things happening in our universe. Now, by the way, it's true not just in the universe. You can go and look at people in the infrared. They look totally different. So, what we're looking at is the heat coming off faces. Notice that the glasses are actually blocking that infrared light pretty efficiently. Animals also look kind of interesting in the infrared. If you want to see more of these kind of pictures, you can go to the Cool Cosmos Infrared Zoo. But again, you're kind of seeing very different patterns of how heat is emerging from these animals, including us, versus our visible light that's mostly reflected. So in astronomy, we've been able to develop infrared detector technologies. These are advanced technology. It's not like the CCD camera in your phone. This particular device here, which is called a Hawaii 2RG, this was a detector that we put in an instrument that we built for the Magellan telescopes, which is over here on the right. And I will say that this detector, which I did hold in my hand, cost more than my house, which made me extremely nervous when I was holding it in my hands. These kind of detectors are made out of exotic elements, things like mercury, cadmium, tellurium, and they're grown as full crystals. And so this is a very advanced kind of technology. But these particular materials are highly sensitive to infrared light. And so it allows us to get these pictures of our sky in the infrared that we can't normally see either with our eyes or with standard optical instrumentation, which is the kind of instrumentation that was around during the 1960s, 70s, and 80s. So once these infrared detectors got into full use, we started to see all kinds of brown dwarfs. And so in the first discoveries were made kind of in the mid 1990s, not too soon before this lecture series started off. The first discoveries included this very faint companion to a star called Gliese 229, which is the very creative name for the 229th star in the Gliese catalog. And B means it's this faint B component. This is actually a picture taken by the Hubble Space Telescope. Around the same time, a couple of young brown dwarfs were found, one called PPL15, one called TD1. These were both found in the Pleiades cluster. You can kind of see the Pleiades in the background here. These first discoveries were made by doing very targeted searches, right? They looked for young brown dwarfs because they knew they would be hotter and therefore brighter. And for Gliese 229b, they looked around the faintest stars to look for even fainter companions to see if we can push down the brightness. So these are very targeted searches to look, it still, took a little bit of luck to do there, but looking for the best chance of finding these companions. Shortly afterward, the first infrared sky surveys came online, and these include the 2-micron all-sky survey, or 2MASS, which is the one I worked on in my thesis, but also the Sloan Digital Sky Survey, which is still continuing, and the Wide Field Infrared Survey Explorer, which is also still continuing since 2010. And all of these telescopes are able to do either full sky or mostly sky surveys of the night sky at these infrared wavelengths. And as a result, they were the first ones to really identify these brown dwarfs in large numbers. Now, I want to give you all a chance to find a brown dwarf because it's so exciting to do. And so I'm going to show you a pair of images here, one taken in the visible and one taken in the infrared. And based on what I've just been telling you, I want you to figure out where is the brown dwarf in the image. Now I'm showing these images reverse. So the stars are in black and the sky is in white. It's just a little bit easier to see the stars in this way. So here's our visible light image. And I'm going to flip over to our infrared light image. All right, I'm going to go back to the visible light image. You can see the stars are basically in the same place. And then I'm going to go to the infrared light image. Some of you are like, I have no idea. Actually, I'm looking at Andrew. He's like shaking his head. No, I have no idea where that is. All right. So the best way we can do this, in which I did, by the way, as a graduate student, is to flip back and forth between these very fast. This is the technique was developed way back in the 1940s by Luyten. And hopefully by doing this over and over, you start to see something that's there in one image, but not in the other. And if you still can't see it, good thing is that sometimes astronomy puts a big circle on the object you're looking for, right? So this thing that I've circled in the infrared image, very nice and bright, easy to detect, is not there in the visible image, right? Infrared, visible. This is an invisible star, right? We can't see it in these visible light images, but we can see it in the infrared. And that's why we're talking about the invisible world of the universe, right? These are stars that we literally cannot see at visible light wavelengths because they are so cold. And we need to have these infrared detectors to find them. All right, so all of that really started kicking in. Again, I was very fortunate to be on kind of the first wave of that when those surveys were coming on. 2MASS was just coming online. I was a little baby graduate student. I got to kind of jump in on that as that was happening. And over the last 20 years or so, we've been finding many thousands of these brown dwarfs. These are no longer rare objects. These are objects that we know exist in all kinds of different environments. Certainly in young clusters, as some of our closest neighbors. We see them as stellar companions. We see them at the farthest reaches of the galaxy. We call these halo brown dwarfs. And then we just see them everywhere. They're just kind of floating around in all kinds of places, right? Brown dwarfs are just exceedingly very common. I want to show you a quick movie here that was made by my colleague, Jacqueline Verity, actually one of my graduate students, Jacqueline Verity, who's now a senior researcher at the American Museum of Natural History. This is a simulation we're pulling out from our solar system to look at our sun's nearest neighbors. And pretty soon here, we're going to start turning on all of the nearest neighbors that happen to be brown dwarfs. And those are all the red dots. All right. So, and these are discoveries, I think, made as of about 5 or 6 years ago. So this is even not the closest list, right? This is just a subset. We're also now turning on some of the exoplanets that are being found around our solar system. But you can see that brown dwarfs are just literally in all directions and in everywhere in all places. And they're also, so there's a lot of them. And remember that the whole motivation for this was to say, oh, maybe there's enough of them to be dark matter. Now, even before we found them, we knew that that wasn't going to be the case, because if you go 30 years without finding a brown dwarf, they're probably not common enough. And in fact, in order for brown dwarfs to be dark matter, they would have to be about 20,000 times as common as normal stars, 20,000 times. And in reality, they're about roughly the same in number. In fact, probably a little bit less, maybe something like 30 or 50% of all of the stars in the galaxy are these brown dwarfs. So nowhere near enough for dark matter. Sorry, no Nobel Prize, too bad. However, 30 to 50% of all the stars in the galaxy is a pretty amazing new population, right? That's a huge number. And so even if we're not going to get a Nobel Prize out of this, I think it's something that we are still very excited about, because it's this grand population that's out there, and we are still learning some interesting things about it. Now, I want to kind of talk about some of the highlights of some of these discoveries. So again, I mentioned that we found all these brown dwarfs. One of the things we found is that even though they are not 20,000 of them for every star, there are quite a few, and some of them are our nearest neighbors. And so this is a nice graphic that was put together by the Ursa IPAC team, looking at some of the recent discoveries, mostly made with the WISE survey. You can see the WISE in front of the name here. These three systems here, all of which lie within about 6 light years of the sun, actually at some point they did, we'll talk about that in just a moment, have been discovered just in the last 10 years, all right? Compare that to previously the closest stars we knew were Alpha Centauri A and B, which you can see with your eye, so no one can claim credit for that, and Proxima Centauri, which was discovered back in 1917, and then Barnard Star, which was discovered in 1916. So 100 years went by, and then suddenly we started finding all sorts of new neighbors, right? That's the power of looking at the universe in the infrared and finding these new nearby things. Now, if you're looking closely at this figure, you'll say, wait a second, wait, there's a star system that's in the Oort cloud? I haven't heard about this. What's going on? That is a star called Schultz's star. And that was its location about 70,000 years ago. So right now, the star is actually a bit further away. It's about 10 light years away. About 20 light years away, excuse me. But when we discovered this star, we found that it was moving in a very radial direction. It was basically moving straight away from us. And my colleague, Eric Mamachek, calculated out how close the star would have been as it passed by the sun. And it turned out that that was really quite close, about 50,000 astronomical units. 1 astronomical unit is the distance between the Earth and the sun. So it's well outside our planetary system, but it's still within the sort of distributed distribution of objects that we call the Oort cloud, which are probably the source of our long-term period comets and things that got thrown out of the solar system early on in its formation. So this star system passed close enough by that it could have passed through this Oort cloud and, could have also perturbed some of those Oort cloud objects. Now, we're going to have to wait 2 million years for those objects to fall into the solar system. So don't hold your breath. Don't worry, freak out yet. But the fact that this system, which we only recently discovered, may have had a very close interaction with our solar system is a really fascinating discovery. And it points to that perhaps there's other such systems out there that we're still waiting to find. All right. So really nearby things, that's very exciting. We're also finding that some of these objects are very cold. So another one of those very nearby objects that was discovered by my colleague Kevin Luman at Penn State, he found that this object was about 250 Kelvin based on its spectral energy distribution. Now, for those of you who are not familiar with the Kelvin scale, if you are currently experiencing 250 Kelvin, you need to get out of the freezer because it's really cold in there. All right, 250 Kelvin is below freezing. So we're talking about a star whose temperature is below the water freezing limit, right? That really pushes the definition of star, I'd say, right? And it's because it's just had all this time to radiate its heat away, and it's just cooled off to this very low temperature, right? So 250 Kelvin, quite an amazing extreme low temperature. Now, when we get to these low temperatures, we start to make some comparisons to our planets in our solar system, because the giant planets in our solar system have temperatures that are in the order of 100 Kelvin or so. Saturn, for example, is about 90 Kelvin at its surface. And so if we look at the spectrum of Saturn, and spectrum is taking the light and spreading it out as a function of wavelength, and that gives a pattern that's shown here. This is the infrared spectrum of Saturn, right? When we look at one of the brown dwarfs that I love, which is a T-dwarf, and maybe in the question I can talk about the differences between T-dwarfs and L-dwarfs and stuff like that, you'll notice that the spectrum looks very similar, right? Same kind of little peaks, same kind of patterns. These are not the usual kind of very smooth round curves that we see for stellar spectra. These are highly structured, and that's in large part due to their very low temperatures. So we really are looking at planetary-like atmospheres because these objects are so cold. Now, what shapes these spectra, what produces these very strong features, is the presence of molecules in their atmosphere. And brown dwarfs host a ton of molecules, some of which are very familiar to us, stuff like water and methane and carbon dioxide. And other molecules which may be less familiar to us, like iron hydride and titanium oxide, stuff like that. All of these are absorbing light in the atmosphere over broad wavelengths, broad bands of wavelengths. And they produce these very broad features you see in the spectra of these objects. So we can identify the colors and identify the chemical makeup based on these spectral properties. Now, it's not just gas molecules like this that turn out to be in brown dwarf atmospheres, because when you think about elements beside or states of matter besides gas, right, we can consider things like liquids and solids. We usually don't think about liquids and solids for stars because the atmospheres are so hot. But things do freeze at certain temperatures. And of course, what temperature they freeze at depends on the kind of object you're looking at. So here I'm showing some vaporization temperatures. This is going from gas to either liquid or solid of some common materials. And you can see the temperatures here. Iron kind of freezes out at 2800 Kelvin, ensitite at 1800 Celsius, excuse me, and water at about 100 degrees Celsius. Now, I'm saying these are the temperatures that you vaporize something, but you can also think of it the other way, is that these are the temperatures, if iron was a gas, it would turn into something like a liquid or solid. And as I mentioned, brown dwarfs can be very cold. And in fact, many of these objects have condensates of these common materials. And in fact, here are some examples of the condensates that we know exist in these atmospheres, based both on theoretical models and also direct observations of the condensate materials themselves. So all kinds of minerals like perovskite and corundum and ensitite, even molten iron is present probably in these atmospheres. My colleague up there at Silicon Valley at NASA Ames, Mark Marley, likes to consider these as floating piles of dirt. But it's dirt with some riches, because those of you who might know your gems know that corundum can also be found in nature in gem form. Things like rubies and sapphires and paparachas are examples of corundum, aluminum oxides. So, not only do we have dirt, but we also have lots of gems. So perhaps we should send a mission out to do some mining out there. But all of this stuff, these gases and these condensates, mean that the atmospheres of brown dwarfs are extremely complex, right? They have lots of different materials that are condensing out them. This is a set of models from another colleague of ours, Katerina Lauders, showing that as you go from the right to the left, hot temperatures to cool temperatures, you start getting all kinds of different clouds of condensate material. So starting off with things that are hard to melt, like metals and minerals, to things that are easier to melt, like salts, to eventually stuff like water and ammonium, things that we see in the atmospheres of Jupiter. All right. So a much more complex atmosphere than just a simple black body that we usually treat with stellar atmospheres. Now, those of you in San Francisco know all about clouds. I know you do. And you know that clouds are complicated, right? They're not just a uniform, spread of material, right? They can have all sorts of different beautiful structures. You could have fogs, you can have just rain, right? You could have just beautiful fluffy clouds up in the atmosphere. And that's just water, right? We're only talking about water clouds in the Earth, and you already have this very diverse set of properties. So we have to also think about these diversity in the atmospheres of brown dwarfs. In addition, we know that the planets, which have clouds of condensates, again, stuff like ammonium and other materials like that, form structures on the surface of the planet. So this is a beautiful ground-based amateur videos of Jupiter taken over the course of several hours, showing just the gorgeous structures of clouds that are on Jupiter. Different cloud layers you see, obviously the Great Red Spot, which is itself a whole storm of clouds and disruption, right? This is not just a uniform sphere. This is a much more complicated thing. Now, we would love to get a picture like that of brown dwarfs. The problem is they are much further than Jupiter, right? They're way outside our solar system. And so this is what we would love to see, but this is what we actually see, little point of light. But one thing we can do is taking advantage of the fact that as an object like a planet rotates, we're seeing different sides of those clouds. We could study clouds by looking at how that light changes with time. And that's exactly what's been done by many groups, studying the light curves of these brown dwarfs. And you get some very beautiful periodic changes that correspond to the structure of the clouds that are in the brown dwarf atmosphere. All right. So instead of being able to look across the surface, we just wait for the surface to come to us by looking over time. And we're able to kind of build up this kind of at least longitudinal map of how the clouds are distributed on the surface. Now, you can go even further. This is a great piece of work by my colleague Ian Crossfield at University of Kansas. He, instead of looking at just photometry, just brightness measurements, he did very high resolution spectra over time. And using that, he's able to actually build a whole map of the cloud structures on the planet. So this is one particular very bright and very nearby brown dwarf called Lumen 16b, discovered by Kevin Lumen. And what you see is as they've monitored this source over the course of its whole rotation period, they're able actually to map the bright and dark spots that correspond to likely places where you have gaps in the clouds and really thick clouds. So this is a map of another star that we can't actually resolve, but we can do it by monitoring it over time. Now, I've been comparing brown dwarfs to planets, and in fact, brown dwarfs really do blur the line between stars and planets. And I'll give just a couple examples here. So this is two systems that we know and love quite a lot. One on the left, 2MASS 1207, is a binary system that consists of a brown dwarf with a faint companion to it, and we can estimate the mass of that to be somewhere between 3 and 10 times the mass of Jupiter. And its temperature is about 1600 degrees Kelvin. So very cold, very low mass, right in the planetary mass regime. On the right is a very famous directly imaged exoplanet system called HR 8789. There are 4 planets orbiting around the star, which is kind of blocked out here because we're blocking the light of the star to see them. These planets have roughly the same masses, 6 to 10 Jupiter masses. They're a little bit cooler because it's a little bit older of a system. But for all intents and purposes, the physical properties of these objects are basically the same as these objects. So which ones are planets, right? How do we define which one's a planet? In fact, even experts can't agree. So way back several years ago, we had a meeting where we were reporting all these discoveries, and we just did some polls, and we said, well, what would you call this object? And even those of us who work in the field and study these intensely don't actually all agree on whether this object here, this 1207b, is a brown dwarf, a planet, or if we had to come up with a completely new class to explain it, right? So we are really blurring what is a planet, what is the star, based on these discoveries, because they sit right across that boundary. And of course, Andrew mentioned that another important thing about the intersection of planets and brown dwarfs is that brown dwarfs can also have planets themselves. And I think one of the most famous example of almost a brown dwarf is this TRAPPIST-1 system. This is a system where we have found these 7 planets, all roughly around the size of the Earth, all found by the transit method. So they pass in front of the star and block the light out for a short period of time. All of these planets are orbiting very closely to a star that's only 8% the mass of the sun. So right close to that hydrogen burning limit. And yet it has these beautiful sets of planets, and potentially 3 of these are in the right place to get just the right radiation from its star to maybe have water on surface. There's a lot of hedges there because we don't really know until we get a measurement of the surface in the atmosphere. Now, if you look at all of the potentially habitable planets, and potentially habitable has a kind of very precise definition here, that they have the right amount of energy coming from their host star to have liquid water potentially on their surfaces. There's something like 21 of these systems that are currently known, and these are nicely compiled by the University of Puerto Rico at Arecibo's Planetary Habitability Lab. Of those 21 systems, 7 of them orbit these extremely low mass right at the boundary between brown dwarfs and stars limit. So if a lot of these habitable worlds are found just above the hydrogen burning limit, a lot of us are starting to think about, what about below the hydrogen burning limit? Can you find even more of these planetary systems at these lower masses? And there's several projects that are doing that. One of the ones that I'm involved with is called Speculus, the Search for Habitable Planets Eclipsing Ultra-Cool Stars, which sounds very tortured until you learn that speculoos is a type of cookie in Belgium, right? They like to name their projects after food. Think TRAPPIST, right? Those of you who know about TRAPPIST will know what I'm talking about, all right? So this is one of the projects that is looking at individual brown dwarfs and low mass stars to look for these signals of transits. And I suspect in the next few years, we're going to be having a few more of these discoveries that actually pass below the hydrogen burning limit. We'll be finding our first brown dwarf exoplanetary systems. Okay, so one more thing I want to bring up about that's interesting in brown dwarfs is that I mentioned that these are really small, very compact. They turn out to be the densest hydrogen objects in the universe. This is a map showing the average density of objects from stars, the giant planets, down to low mass planets. And just for comparison, I've plotted the average density of some common things like Earth and water, and the densest metal, which is osmium. And you'll notice that the brown dwarfs, which sit right at the boundary between stars and planets, are right at the peak of this density. They are denser than any of these objects that are on this chart, about 100 grams per cubic centimeter on average. And of course, things get denser toward the middle, so their core densities can be up to 1,000 grams per cubic centimeter or more. Now, when we get to these very high densities, you end up getting to very exotic states of matter, particularly when we talk about hydrogen. This is a phase diagram. You might remember this from your high school chemistry or college chemistry class. This is showing pressure versus temperature, and the various different kinds of states that hydrogen can be in these different cases. So, kind of average temperatures, low pressures, it's usually a gas. When you get to higher, colder temperatures, it freezes out. When you get to higher temperatures, it becomes a plasma. When you get to really high pressures, you start to get into these exotic states of matter where hydrogen starts to act like a metal, something that can conduct electricity. It can start to become a metallic liquid at high enough temperatures and high enough pressures. Now, that is the state where we think the core of Jupiter is. If I put in the pressure diagram for brown dwarfs, notice that it extends right off this chart. The core pressures of a brown dwarf is something like 100 billion times the atmospheric pressure here on Earth from our atmosphere. And this is a region where we really don't have good measurements. And in fact, the kinds of experiments that can make the most high pressure measurements are the compression ignition fusion facility that's up there in Northern California, where they actually taking lasers and compressing a little pellet to see if we can stimulate fusion. When you do that, you really increase the pressure very dramatically. And so you are able to get to pretty high pressures, almost as high as the interiors of brown dwarfs. So this black line is the pressure of one of these first brown dwarfs, Lisa 229b. It gets up to about 200 billion times the atmospheric pressure. And these experiments can get about to half of that. You can also get to pretty high densities, but all of these happen at very high temperatures because, again, they're trying to make fusion happen. So even though we have these experiments, they're actually not measuring the conditions that we see in the interiors of brown dwarfs. And so there's still a lot of work to be done to see, is there a way we can actually laboratory study these kind of environments? Right now, it's only the brown dwarfs that tell us what these kind of conditions are. So they're a place for really exotic matter. All right, to conclude up, I wanted to kind of give a little bit of what's ahead and highlight a little bit of kind of the work that we're going on in my own lab. The National Academy of Sciences has just released the Astro 2020 Decadal Review, and this is publicly available. You can access it on your own, and you can see what this committee, which has been composed of astronomers around the country, putting in both their ideas, but also kind of congealing those into a set of priorities. They focus on kind of three big areas: the worlds and suns in context, new messengers and new physics, and cosmic ecosystems. And if you look in there, one of the big things that they've been looking at is to try to understand our Milky Way. Like one of the key, and this is actually a quote from the Decadal Survey, one of the key scientific challenges of the next decade will require improvements in our understanding of the Milky Way, its contents, and its environment over space and time, work often referred to as galactic archaeology. Remember that phrase, because you're going to be hearing that a lot in the next decade or so. Well, it turns out brown dwarfs may be really good for this. All right, I mentioned that they're very common. The other thing that's really important is that every brown dwarf that ever formed still exists because they don't die. Stars die because they run out of hydrogen as they fuse it, but these don't fuse hydrogen. So every brown dwarf that has formed since the universe began is still with us and maybe floating around somewhere in our own galaxy. And they'll continue to float around because they just don't do anything. They just cool off. So they'll be around for a long time. They're also very common, as I mentioned. So there's a lot more of these brown dwarfy things than the typical kinds of stars that we study for galactic archaeology. And they change over time, right? They are cooling off. And so very major bulk properties like their luminosities or their radii will actually evolve continuously over time, which means that we can use a temporal piece of information to understand where that brown dwarf was, when it formed, and what were the conditions in which it formed. So we have not just a star in place, but we also have a star in place and time. And that's going to give us a lot more information than we would normally have. Go ahead and skip through a little bit. So I have a couple of students that are working on the sort of initial pathfinders for these. One of these students, Dino Siu, has been looking at the 6D velocities and kinematics of the stars nearest to the sun. The dispersion of those motions tie very directly to how old these populations are. And by looking at how different spectral types, different temperatures are dispersed, we can actually build up a picture of star formation of stars that are in our solar neighborhood over time. So that's one way of getting at that time variable. Another student of mine, Christian Aganze, is working on looking at brown dwarfs at very deep parts of the Milky Way, using the Hubble Space Telescope to kind of make very long pencil bead measurements of these things. These show us how brown dwarfs are distributed in space, which is also related to their ages. So he's been building these both simulations and also machine learning tools to see how brown dwarfs are distributed both in space and time. And then another one of my grad students, Roman Gerasimov, is looking at brown dwarfs in specific old systems called globular clusters. I mentioned Omega Centauri at the beginning of my talk. He's been working on models to predict where brown dwarfs will be in terms of their brightness and colors in these color magnitude diagrams when James Webb is going to be looking at them. So the left side is data that we already have with the Hubble Space Telescope, which doesn't make it to that brown dwarf regime. But on the right side, we have data that we expect to get from the James Webb Space Telescope. And that brings me to the main thing that we're looking forward to, of course, is the James Webb Space Telescope, which I'm very happy to say I've updated my slide to say that it has launched and it is now at L2 and undergoing mirror phasing, which is basically the mirror kind of getting itself lined up to make the sharpest images. And if you want to stay up to date on what Webb status is, there's a beautiful web page that kind of shows where it is in its timeline. It's at the mirror phasing time space right now. James Webb is one of the facilities that we have coming on board in the next few years. It's actually going to be a time of riches in terms of big telescopes. James Webb, we should starting to get data from that as soon as this summer. But we also have other big surveys coming online from the ground. The Legacy of Survey of Space and Time, or LSST, will have first light in the next year or two. That's going to be a tremendously big boost in survey compared to Sloan, for example. And that's going to give us millions of brown dwarfs. Millions of brown dwarfs. It'd be amazing. We can also start to look at fainter brown dwarfs with large telescopes, things like the 30-meter telescope and the Giant Magellanic Telescope are coming online in the next 10 years or so. In space, the Euclid mission and the Nancy Grace Roman Space Telescope are both going to be space survey telescopes, and those are also coming online in the next next year to 5 years. So we're going to have so many facilities to really expand out our sampling of brown dwarfs that this idea of mapping them out in the galaxy is going to be reality quite soon. So I want to thank everyone for joining, and thanks for sticking around for the full hour. I took a full hour to talk. I like to talk about brown dwarfs, you can tell. And I'm happy to pause here and take any questions. And again, thank you very much for listening. I hope you enjoyed it.
Well, thank you so much. Great. We appreciate this marvelous introduction to these amazing objects. And it's now my pleasure to introduce the current astronomy professor at Foothill College. I said I was emeritus, but the person teaching there now is Dr. Jeff Matthews, and he has been curating the questions that you have sent in. And again, I'll remind you that you can ask questions at astronomy@foothill.edu. You can email questions to that email address, astronomy@foothill.edu. And so I'm going to turn things over to Dr. Matthews for the question period.
Thank you, Andy. And I'd like to thank Dr. Burgasser again for speaking this evening. I really enjoyed your talk. And so we've had a lot of questions come in. And so I'll try to keep an eye on further questions coming in as I go through the list here. We're probably not going to have enough time to get to all of them. So my apologies to everybody up front about that. So starting with a question from Les. He says, if I recall correctly, there was a citizen science effort with respect to brown dwarfs. Is that something that you could comment on, brown dwarfs with respect to citizen science?
Yeah, I would be happy to. And I should actually say, Les, I was actually had that as a slide, but I could tell I went over, so I had to do some cutting on the editing on this. The project that you're referring to is one I'm actually involved with, and it's called Backyard Worlds. The mission of that project is to find more of these exotic brown dwarfs, cool brown dwarfs, things that are very old or very metal poor. So kind of as a context, when I was doing this project to do, as a graduate student looking for this new class of brown dwarfs, I literally sat and stared at images of stars for like 6 months. I had to go through 250,000 stars for 6 months to find 13 brown dwarfs. It was very painful. But the technology to do this online is much improved. I did this with pieces of paper, right? Very bad use of paper. Today, we can do a lot of these tools online, and the Backyard Worlds community, which is primarily dominated by amateur astronomers, a lot of our community members have actually helped us build the tools to do this kind of blink comparison, to look for moving sources, to look for faint sources with a beautiful web tool. And it's open for anyone to come in and discover brown dwarfs we've never seen before. And a lot of, in fact, and I should tell you, we actually are observing right now. As soon as I jump off here, I'm going to go to the Lick Observatory through my computer because we are observing right now some of the candidate brown dwarfs that these amateur astronomers have uncovered. And so, yeah, if you're interested in being part of the discovery process, the Backyard Worlds Planet 9 program is one you should take a look at because a lot of the discoveries have been coming from our amateur astronomers, and literally we feel like we're scientists for hire. We just find out these great targets, we point our telescopes at them, we send the data, and they go off into the world. So yeah, amateur astronomers definitely can get involved in this hunt through that Backyard Worlds program. So please take a look at that.
Wow, okay. I will be looking into that.
Great, awesome.
when we're done here. So we've got a question from Scott asking, is there a chance that Planet 9 is a brown dwarf?
Good question. So, so I would say it's probably not, and I'm going to be very hedgy on this because there's been a real concerted effort to find a brown dwarf companion to the sun. And part of the reason is that we see brown dwarf companions to other sun-like stars. Many, as I mentioned, like one of the first brown dwarfs found was a companion to a nearby star. But we found many different kinds of brown dwarf companions to all kinds of stars, and in some cases stars that have their own planetary systems. And so the sun, at some degree, is kind of an abnormal star in the fact that it's by itself. And so, we've often thought that perhaps there is a very faint companion that we just simply can't see with our eyes. Now, at this point, this kind of search space for that companion has been pretty exhaustive. There are some parts of the sky where it's hard to find a companion to the sun, for example, in the galactic plane, where there's a lot of other stuff that you have to kind of look behind you. That's hard to see. But I would say we've probably ruled out like 95% of the area that we could really say that a sun solar companion could be. And Planet 9 in particular, if it was a brown dwarf, it would have to be an extremely low mass, much lower mass than the brown dwarfs we found so far, to remain invisible to our eyes, because something that's in our solar system, even at what we expect to be the very large distance for Planet 9, so hundreds to thousands of AU away, would be really bright. And I mentioned earlier this star called Schultz's star that had this close passing at about 50,000 AU from the sun. That star, by the way, would still have been invisible to the naked eye. So I know, like, when press came out of that, there was kind of a Cro-Magnon man looking up at this bright star. We wouldn't have seen it because it's still invisible, even at that close proximity. But in the infrared, it would have been a first magnitude star. So no hiding that. That's super bright in the infrared. And so anything that's kind of the kinds of brown dwarfs we've seen so far, all the way down to about 250 Kelvin, we've basically ruled out because we would have seen that quite clearly. So it's possible it's lower mass and fainter than that. And of course, most of the estimates for what Planet 9 are kind of in the tens of Earth mass range. But that's probably not a brown dwarf. That's more like kind of a super terrestrial object.
Got it. Yeah, that's more similar to the mass of, say, like Neptune or something, right?
Yeah. Yeah, exactly.
Okay, so speaking of, there were some questions about that brown dwarf that passed through the Oort cloud. So from Curtis, we got this question: that brown dwarf that passed through the Oort cloud 70,000 years ago, is there a related extinction event from comets dislodged at that time?
Great question. And there isn't, in part because that only happened 70,000 years ago, blink of an eye. And it actually takes, a million or so years for the comets that are perturbed way out at that distance to make their way into the solar system. So maybe a future extinction event, but I'm not going to be around for it, fortunately. So we don't have any indication that passage triggered any kind of comet storm or anything like that. Now, that being said, it is certainly possible that a different passing star way back in the past may have been the trigger for a cometary event that would have come in. We don't have, and this is actually another reason why we think Nemesis is an unlikely, so Nemesis is being this potential companion to the sun, that it's unlikely that it's out there because the impact sort of record that we see on all the planets like Mars and the moon and stuff like that, there was an early bombardment phase, but there hasn't been like periodic bombardment phases like that. And so it's unlikely, unless there just happens to be like one star that passed by and maybe triggered just the one wrong comet that came in. The other thing to keep in mind is that the Oort cloud is incredibly sparse. So even as this Schultz's star passed through, even if it passed through the Oort cloud, it probably didn't get close enough to any of the Oort cloud comets to really perturb them very much. It's just one little brown dwarf. And so the impact parameter is actually quite small compared to the sparsity of the sources out there. So people have done some calculations. It's unlikely that it hasn't triggered yet, and it's unlikely that it will trigger a comet storm, but time will tell.
That's a nice multi-million-year research project for you.
I hope I can get the funding for that.
So taking a little bit of a turn here, I've got a question from, I think this is Unme, saying, I'll take the bait. Why are the spectral types out of order?
Oh, I'm glad you asked that question. So just a reminder, the standard spectral types were O, B, A, F, G, K, M. And then we've now since added with our brown dwarfs L, T, and Y. All right, so I'm going to break this up in two parts. Y, O through M first, and that is the lore of this. And I think Andrew, you might want to jump in case I get something wrong here. You might also know this very well yourself. The very earliest spectral surveys happened back in the end of the 19th century, and these were done with early photographic plates. This was very hard work, and in fact, the folks who actually did the classification was a team of computers who were primarily women who worked at the Harvard Astronomical Observatory. I'm not sure that's the right name of the facility. But in any case, they grouped these up into kind of like and dislike kind of things, and they put them in a nice normal sequence, A through whatever the last letter was, maybe O or P or something like that. And it wasn't until later that we started to understand the connection between the strength of various features in the spectra. So things like the hydrogen lines or the helium lines that are common in normal stars, and how that relates to temperature. And by the time that was figured out and we wanted to kind of organize this into a logical temperature sequence, so many spectra had been classified. To go back and redo it all didn't seem like the best idea. So we just reorganized the letters. Does that sound about right, Andrew?
Yeah, it was one of the women who also did the
Thank you,
modern
yes.
organization. It was Annie Cannon.
Yes.
Who gave us our modern system, but yes.
Yeah, thank you for mentioning Annie Cannon. We've actually have a AAS prize in honor for Annie Cannon for her contributions. But she made the real real physical understanding jump that we need to reorganize these so that they are in a logical temperature sequence. Right. So that's O through M. Right. L, T, and Y were obviously letters that we added in afterwards. You might say, well, why did you continue to just write these in random order? And my PhD advisor, David Kirkpatrick, in his 1999 paper that defined the L dwarfs, actually has a nice little table that goes through and explains why, some letters would work and some letters would not work. Obviously, the letters we already have in our spectral sequence don't work. But there's other letters like V is often used for V magnitude, so that's kind of confusing. There's other kind of letters like that where they actually correspond to kind of strange classes of stars, maybe white dwarfs or unusual variables, stuff like that. And in the end, we were kind of left with something like 4 or 5 letters, which included L, T, Y, and Z, and H, as it turns out. And for whatever reason, H just didn't seem right. And he just chose L, and it stuck. And so when I came along and did the next letter in the sequence, I chose T because it was kind of the next one in the list, and it just stuck, right? So some of the things that happen in astronomy are just because you just keep publishing them, and then people just say, okay, we'll just use T. I will say that at the time there were other letters that were proposed, and we just kind of beat them out. So it's a little bit of a competitive thing. So the L, T, and Y just came in because those were kind of the 3 of the last letters that we could use, and no one wants to use Z yet because that's like the end, right? So you want to save that for the end. We're not quite at the end yet. So it's a complicated history, but it is it's how it's gone.
Well, yeah, and nobody then wants to wrap around, get all the way back to H. Yeah, sounds messy.
We talked about Russian letters for a little while, and we figured we should just keep it kind of simple and yeah.
Okay, so a bunch of people emailed in with questions along this line. So Margaret asked, what is the difference between a gas giant planet like Jupiter and a brown dwarf? So like what ends up being the biggest difference?
That's a great question. And it really depends on if you look at it from an observer's view or a theorist's view. So I will start from the observer's view. And the answer is actually probably not much because we can find brown dwarfs that look a lot like the giant planets like Jupiter. Now, there is a difference in the fact that brown dwarfs are actually in generally much more massive, right? They could be 30, 40, 50, 60 times as massive as Jupiter. And they actually end up being about the same size, just kind of the way that the kind of degeneracy pressure balances out other effects. There's not much change in size when you go from kind of the end of the stellar sequence to somewhere around Jupiter. So they're all about the same size, but that mass makes a difference. If you stick 70 or 60 times the mass of stuff into the same package, you end up with a very dense object that also has a very high surface gravity. And that's kind of the gravitational pull at the surface of the planet. Now, you might say, well, how would you know the gravitational pull? Because you're not actually dropping anything there. But that affects the chemistry at the atmosphere because it increases the pressure at the atmosphere that we see. And so we can see some of those pressure effects in our spectra. So we can see differences between a kind of normal mass brown dwarf and a very light, low mass planet based on these, what we call surface gravity features. But otherwise, the bulk things like the size and often the temperature can be exactly the same. So they do have very strong similarities from an observational perspective. From the theory perspective, right, then that really gets into the question is how do these objects form? And this is where a lot of the debate about what is a planet and what is a star comes into existence. I showed at the very beginning kind of this picture, very basic picture of star formation where you start with a huge low density cloud that collapses under its own gravity, heats up and starts fusion. And we think that most brown dwarfs form the same way, they just don't start the fusion at the end. But there's other ways you can make big objects like that. And that is for giant planets, for example, you could start with a very large rocky core that you might assemble from the rock and ices in the early solar system and the disk of material that forms around a forming star, and then accrete a whole bunch of gas onto that rocky core or icy core, and that makes something like Jupiter. So that's kind of the standard picture for how a planet like Jupiter forms. It's kind of the inside out, whereas a brown dwarf forms from the outside coming in. Now, if it would be great if those were the only two options, but we are very creative scientists, and our colleagues have come up with other ways to form these kind of things. So you could have, for example, the disk that forms around a star fragment under its own weight and collapse into little balls of things. That's kind of a mix between that inside out and outside in, and that could potentially form something that's like a really massive giant planet or a brown dwarf that might eventually get kicked out and float away. There's another example. There's also like cases where, for example, you start with a cloud that's collapsing, but then a really bright star is nearby and it kind of blows away the material, and you're left over with kind of like what's remaining. And that would be a slightly different mode of formation than sort of standard star formation. So as we've just studied this kind of in-between class, we've really had to think hard, is there other ways of making these big balls of gas, right? And it turns out there are. And so now one of the things that we do is to try to understand, for these different ways of forming things, are there predictions that would allow us to distinguish one over the other? So maybe it's whether you have binaries and what those binary properties are. Maybe it's the velocities of these stars. Maybe they get kicked out in different ways if they're formed in different mechanisms. So that's kind of the back and forth that's happened now, right? From the observational side, we look for these little clues. From the theoretical side, we see that there may be some other options. And now it goes back to the observers to see if we can check the predictions. That was a long answer to it. Probably, I hope that was the right answer to the right question, but because it was really about the differences. And so there are differences, both observational and theoretical, but there's also a lot of similarities. And so it's tough to do.
All right, well, we're going to go into the final couple of questions here.
Great.
And so again, my apologies to all the people whose questions we're not going to be able to get to. So Edward asks, red dwarfs tend to have instabilities that reduce the chances of life on planets in the water zone. Are brown dwarfs also unstable?
It's a great question. And in terms of instabilities, I think maybe what is being referred to there is that M dwarfs have really active magnetic fields, and they produce these tremendous flares. They're actually some of the most energetic stellar events that we see. Even these tiny little stars, they produce these massive, massive flares. And of course, when your little host star suddenly doubles in brightness for a little while, that can be very bad for life on the planet, particularly when a whole bunch of high energy charged particles follow it. And so the instabilities I think that are mentioned here are these kind of magnetic flaring events that, yes, can be very disruptive to the planets nearby, particularly because for cool stars, those planets have to be really close to be in the habitable zone. So they're getting kind of the full brunt of that flaring energy. We do know that brown dwarfs, and this is actually one of the surprising things that we found, is that brown dwarfs have very strong magnetic fields. They can be as strong or stronger than some of these M dwarf stars that show these flares. And some of these brown dwarfs, particularly when they're young, do undergo quite a lot of flaring. But as they get older and they cool off, the atmospheres actually kind of decouple from the magnetic fields. It's kind of like for something like the sun, you see these beautiful spots and these kind of, beautiful sort of arcs of material that come out when there are magnetic flares. That's because the material is so hot, it's highly ionized. So it's really attached to those magnetic fields quite strongly. But these atmospheres become very neutral. And so that there's not many charged particles to kind of interact with the magnetic fields. And so they actually become quite quiescent. They don't really flare that much. In fact, when we look at the rate of flaring, it drops off really fast once we get to the end of the M dwarf sequence and kind of the beginning of the L dwarfs. Now, there are some exceptions, and actually I've studied a couple of like really bizarro exceptions that are very active, but for no reason whatsoever. But for the most part, most of the brown dwarfs, the cool brown dwarfs you study, are highly inactive. They have some radio emission. That's not particularly dangerous, but they don't have any of this X-ray or high energy optical radiation that we associate with massive M dwarf flares. So in that sense, that makes them a little safer to be around. There is one downside, though, to living around a brown dwarf, is that the brown dwarf is always cooling. So the habitable zone moves over time and it moves inward. So your planet might be perfectly fine when the brown dwarf is an L dwarf, but when it becomes a T dwarf, you might be frozen out. And so there is a question about the long-term stability of habitable zones and how long a planet will actually be in there. And, is that long enough for life to arise and figure out a way to get out of that situation? That's a big question. But, in terms of the flaring, it's not so bad, but there are other issues that we have to worry about in terms of habitability around these stars.
Got it. Okay. And so now here we have our final question. This is almost looping back to where it all began. To that question about the possibility of brown dwarfs being the dark matter. So got this question from Hans asking, could there be even smaller things, that are like 0.01 times the size of the sun, but just hundreds and thousands of them?
So the answer is it's still possible, right? So we, our measurements today are able to find, things that are like 1% of the mass of the sun, for example. That's kind of the limit that we can do for objects in the field because they get too cold, or very young objects which are warmer, but they're still not as luminous if they're very low mass like that. It is always, and I should say, in terms of like the numbers of stars as a function of mass, it's still, it's pretty flat, and it actually looks like it's coming down a little bit as we get to these very low masses, although the uncertainties are very large, right? It's hard to build big samples of these. So really constraining whether you get lots more or it's all dying off, it's still an unknown question. Now, it is possible, and in fact, it may be possible that the numbers ramp up not because you have brown dwarfs, but maybe this is the upper mass end of planets that somehow get kicked out of their solar systems, right? There's always this question of, we see an object and we don't necessarily know where it came from. And so there have been some early studies with microlensing, which is a technique looking for like small mass things that temporarily brighten a star that it passes either in front of or kind of close to, again, through the gravitational effect. And there's been some early results that suggested that there were a lot of really small mass brown dwarfs that started to get big enough where you'd start to wonder if this is at least a component of dark matter. I should say that those early results, and this happened around 2011, 2012, most of those have kind of gone away as we've gotten larger samples. So what invariably happens in astronomy is you have a small sample, it produces this really interesting result. If you say, oh, this is interesting, let's follow it up. And then you get more measurements and it turns out it goes away. It's really sad. But so far, the real big boost in numbers at small masses seems to have kind of dampened down. But it's still small numbers. And so one of the missions I mentioned at the end, the WFIRST mission, one of its main objectives is to do a microlensing survey that's going to get down to these very low masses. And just to kind of give context for this, to find low mass microlenses, they happen really quickly. So the lower the mass, the shorter the microlens event. And so you're looking at events that might take like a couple days or even a day. And so you need to be really on top of monitoring to do this. And that's what WFIRST is going to do very well. So that survey should really answer this question. Is there a sudden jump up in the number of very, very low mass things? That we'll see. My guess, my bet, maybe I should bet with someone on this, is that we're not going to see kind of a big population of low mass things, and dark matter is still going to be something else.
Nobel Prize is still there to be won.
Still there to won. Anyone, take it.
Thank you so much for a fascinating exploration of really not just new worlds, but a new world of discovery. And you've been part of it. So it's very exciting to have you share all that with us. Thank you very much.
Thank you very much for the invitation.
All right. And we will say to everyone else, please join us again. Our next talk in this series will be April 27th, when Australia's Charles Lineweaver will be our speaker. And he always has some interesting things to say. For all of us at the Silicon Valley Astronomy Lectures, thank you very much for being part of our event tonight, and good night.